Okay, sorry for the delay, you guys. What I need you guys to do is, one, put your phones away, get all those tucked away. Hint, hint, gentlemen. Again, I want to remind you of two things. One, Sierra, I don't know if you saw this on the video, but I want to remind all of you, we decided, and I'm okay with this, we're going to do homeworks by completion. That's fine by me.
Yeah.
All you need to do is turn it in. So there was nothing due today, right? I hadn't assigned any homework. I have another homework for the weekend. So that means when you come to class next time, right away, I'm going to say, hey, get out your homework. You're going to have to show me that you did it. Like, yep, you got it, full points, full points, full points. Or if you don't have it, then it's late, right? Then I just need you to do it, turn it into me later, and I can give you half credit. All you need to do is show me that you did it, right? Don't try and write some numbers down and say, yep, I did the homework. One, I'm going to get real annoyed with you if you're trying to pull a fast one on me. But ultimately, you're shooting yourself in the foot because you're not doing the practice, which, again, you guys told me you wanted to help learn material. So you're going to shoot yourself in the foot because you're not doing the practice that you're supposed to be building that skill set. That's fine. But I need you to just be honest and genuinely attempt it, right? Show me that you did it, and then we'll go through it in class, right? We'll walk through, like, I'll probably ask, like, which ones didn't you get? A lot of you might have the same answer, so we'll go through that. So I wanted to remind that on homeworks. Guys, are we all on the same page? Yes. The second thing I want to mention, did you see a bunch of grades go in Power School?
No.
Yeah. No?
Yeah. Where do you think I am?
You saw them, right?
You at the Power School app?
Well, I don't know if it emails you, right?
When did you put them in?
Last night, I think.
Not only my grade.
I gave you a bunch. What was it, Aiden?
I just had the Power School app, so it just showed me that you updated it.
What I gave everybody is basically Unit 1 participation, right? Part of that is because I'm supposed to give grades, right, feedback to students via grades, like every week. Well, we didn't have a lot of assignments week 1 or Unit 1. So what I did is I just gave everyone discussion participation. Now that we're doing homeworks, we're going to be fine, right? But if you see all those, there was like 6 weeks worth of discussion. That was just basically participation points. So you basically got 3 points. So I just want you to be aware if you saw all these notifications or all these grades pop up, that's what I was doing. And in virtual students, you got the same thing. So I wanted to clarify what was going on there. Today, there was 1, 2C in your workbook, that big packet of sheets. 2C was one of them I wanted to do. We didn't have time. I wanted to do that one quickly. We'll finish that. Then we're actually going to start talking about Newton's third law. We'll go through Newton's third law, and then we might have some free time at the end. You can start get started on your homework. We'll kind of see how it goes. I was kind of basing this on being a pretty light day. I didn't want to do too much. It's Friday.
It was game day.
So, what I need you guys to do, is in your student workbooks that you have, right, 2.C. That's the one that I wanted to do. We didn't have time. So I want that to be what you focus on doing. Remember at the end of last class, I was talking about free body diagrams. Do you remember that? That weird scenario where a very particular way to draw forces. Now, it's particular partially so that everyone is on the same page. Everybody knows the rules. Everybody can understand it. Well, also, it's AP. It's very particular. Right? If you have some object, you can draw it as a dot. I want to draw all my forces that act on the object. Would I ever want to draw this, Fx, Fy, if they're the same force, do I ever draw the components of a force? No. You never draw the components. These are imaginary. This is we took a force and we're going to break it into pieces to do our math. I never do this. I want to draw the actual force. Right? You will almost always assume that this is xy, x positive, y positive. It's a good habit to write this down, but you don't have to, as long as you always do this. Whenever you're looking at your paper, this is always positive x direction, positive y direction. It's also how we think about the world, right? Up is positive, down is negative. But just so you know, no. We live in a 3D world.
So far, the world's only been negative.
That's depressing, Brody.
I mean, but
Not
after.
wrong. It's 2020.
Oh, I got you. The 2020 memes. I've seen some funny ones.
You thought you were depressed.
Yeah, I thought you were talking about like my life has been negative always.
Like your entire life.
Right? You said so far the world has been only
You got
negative.
to email the school guidance.
I was like, dang.
I knew
Counselors,
exactly
get on this guy.
I knew exactly. He's about to
Do
make
you
me take the
understand
survey.
why I interpret it that way?
Yes.
I never interpreted it that way. I seriously
And you just
like,
had your
yes,
physics
bro.
thing.
Yes, son.
Evan, I'm sorry.
Did you say it was 2C?
2C, yes, I apologize. So that's what I want you guys, again, remember this, because that's what this 2C, this worksheet is. It tells you some forces acting. You got to start, we're going to start drawing our free body diagrams. Do you not have it?
What?
2C? You do? Okay. I thought you needed to print one or something.
I don't like the name Student Workbook. I think we should change it.
To what? Stupid workbook?
I don't know.
Yeah.
Is that what you're saying?
No. I just,
Oh, you said you didn't. Okay.
I don't like the name Student Workbook.
What do you want to call it?
I don't know.
Student.
Big old packet?
Big old package.
Look at
I
this.
Big boy.
suppose we could do that.
No, hey.
We can write a letter to AP.
You know, big old packet.
This isn't a big old package.
Is he the math teacher? Do you have Augustine? You were the one that told me like you have everything for the class printed out because he was assuming we'd be shut down. Yeah, she had a huge stack, and I was like, "What are you doing, Maggie?" She's like, "Oh, this is my calc class."
That was like freaking something Leslie Knope or Amy Santiago would make.
Two great shows.
I wanted two.
I mean,
Dude, I want to. This is only honors break. This is only honors break.
That's
Still
bonkers.
bonkers.
Do you have a Gus
Where did he get all that free time to do
Can you imagine printing that much for one student and then having to repeat it for the other 40?
No, there's only like,
That's only 1 and 2.
well,
That must
there's
take
14 in the original class,
Okay.
and people are
Right.
dropping like
Never in my
that.
you're on honors
Really?
now, correct?
I think
It's a.
possibly 2 more students could drop in the next week.
Is it?
That's not as smart as you, Josh.
Maybe. Okay.
Because they don't have to see.
Yeah, BC's not.
I am double
Yeah, but
I'm double
one
up
student
by
on
sophomore, that's why.
I'm pretty sure.
I took algebra. I took algebra 2 honors, and actually my first something, and they had me
At
in
least 2.
Are you feeling okay in it? Yeah.
when you're already so far
I'm a
negative,
math
what's another
science
negative?
person.
Okay, that's your thing.
Another-
Okay, that's good. AP Calc is a
But
great
my
class.
physics, not physics, but
Oh man,
Negatives in your life,
I'm more of a
then you
chemistry
should-
person.
fair enough. I'm definitely more physics than I am chemistry. That's fair. Everyone's got their quirk or the thing that comes easier, or that at least they're interested in, so then they work harder and do better.
Yeah, that's why like, for the past 3 years I kind of figured out what I want to do.
Yeah.
What is it? Chemical engineering? Yeah, I was mechanical engineering. I'm very familiar with engineering if you ever have questions
I
about
do,
what you
I do
do.
want to talk on it.
Yeah, feel free to like shoot me an email and ask, like, hey, can I stop in if you want to do it more towards like semester break, like towards the
It
end of the
doesn't
year.
matter, I just want to talk about it sometime.
Yeah, whenever
Just
you
because
want.
you're like the only person that would know anything.
Yeah, yeah. just shoot me an email whatever time you decide, like, yeah, I want to come in after school, as long as you give me some heads up, I can plan for that. ISA would work. We wouldn't have, like, time to just sit and chat. But yeah, just email me sometime whenever you want. Just let me know and I can figure out a time we can do that. Okay, guys, I'm sorry I didn't do a great job helping you guys focus. Again, I want you guys to refocus on 2C. The first part is making a free body diagram, right? And then the bottom is a little weird. You're going to explain their math. They're going to do the math to figure this problem out. You're going to explain what each step is doing and why it is. That one's that's new, but AP really likes not derivations, but solution procedures and understanding what's going on. So that's what that is. And the backside, I want you to try it. That one's a little harder. It's, again, focused on scientific arguments. Correcting a certain statement, and then explaining why you're correcting it. So I want you to at least attempt those. I can come around and answer questions if you want, but I want you to work through that, and then we'll talk about it.
2C. Unit 2 dynamics. Page 33.
How to get started on the free body diagram.
Yeah, I was just reading.
Okay.
You see, they're all wrong because it's supposed to be F equals M.
That's right.
And all of these have like two
So this one says literally their first step, what the math they're doing is they're writing this equation. And they're going to explain, hey, we're going to start with Newton's second law,
But I didn't get
which is
that.
you're just saying what you did here. Well, the next step, what did they do? They changed the left side into, instead of saying the sum of the forces in the y direction, they wrote it in, right? Fn is a positive direction, so they wrote it positive, minus Fg. So you would explain the sum of the forces in the y direction is the normal force minus, yes, well,
You know what I'm excited for?
you just literally described what did they do in like step. They said, the sum of the forces in the y direction is equal to the normal force in the positive direction minus gravitational force in the negative. Basically just add commentary on what they're doing.
I don't remember who it was though.
You guys understand that second part?
I don't understand it, Paul.
You guys, the second part, right? The equation. On the left side, they do the math for you. They solve it. What you need to do is comment on what they did in each step. So the first step, they wrote F equals ma. Well, they comment like, yep, we start with Newton's second law, which says sum of the forces is equal to the mass times the acceleration. Well, if you look at their next step, what did they do? They changed some of the forces to be Fn minus Fg. So you're going to comment, the only force in the y direction are the normal force in the positive direction and the gravitational force in the negative direction. You're literally just commenting what they did. The next section, they cross out the acceleration and set it to 0. You're going to comment, there is no change in motion in the y direction, so ay equals 0. You're adding commentary on the math that they're doing. You're basically explaining the math steps that they're doing. And the backside, again, is a scientific argument. You got to critique and then correct. AP's really big on scientific reasoning and thinking and scientific arguments. That help?
The concept, but
Again, what did they do here?
I don't know what they're doing.
From
I
here
get
to here.
the idea that they're breaking it down like it's algebraic equation.
Yeah, so you literally explain here, the sum of the forces is equal to normal force minus gravitational force. Just write that out. You're commenting on what actually was done here. You get that? Oh. I don't know how to explain it. Okay, Michael. From here, what are you going to do to simplify this?
I thought that was simplified.
No, this is saying that some of them force in the y direction. What forces are in the y direction? This is the y direction. What forces are going up and down on here? Okay, you gotta make sure to label these. I gave you the answer, right? Too fuzzy, what do you mean?
Like the picture the other day when I was writing that in, when I was copying it, it was too fuzzy.
Oh, I don't want you to copy, I want you to solve the problem. So you know you're pushing on it, right? FP. So this force is called FP, force push. This is force friction. This is the gravitational force. That's the normal force. So this is Fn. That's Fn. You push to the right, that's that force, so that's called, call it Fp. And you got force of friction or friction. So in the y direction, you only have these two forces. To add vectors together, they're in the opposite direction, you subtract. So what they did here is they said the sum of the forces in the y direction is Fn minus Fg. So that's literally what you would write. The sum of the forces is actually equal to Fn minus Fg. You just added commentary on what you did to get that step. And then you just keep going.
Yeah, I thought it'd be like this.
Well, his arms are parallel. So his hands are reaching this way. He pushes by applying force directly to the right. This is FP, the force of push. Right? You know it's a rough surface. So this is where you have friction. And friction pushes backwards.
Oh,
So you draw an arrow backwards, that's the force of friction. Now you have the force of gravity, I think. Right? Gravity is always acting on this. So this would be F sub g, right? Force of gravity.
oh, you said substitute. I don't know what I'm writing.
Well, that was Ff, right? Force friction.
Yeah. You said put like in a sub form.
Yeah, kind of like I have that F little g.
Yeah.
That's some standard notation for forces.
Yeah.
And then what else do you need? If this is true, the rock would be going to the center of the ice. What holds it up? Do you remember what we call that force? We haven't talked about it a lot.
I don't remember.
It's normal force. So there's a force that pushes up. That's basically the ground supporting the rock. That'd be force normal or F. That would be all the forces that are acting. Then you go through and do your math in the y direction. I want to finish this because I want to do that yesterday. We're doing Newton's third law, so we're going to learn about that. And then I think I'm going to give you guys some time. We should have time to start your homework. We can do a couple together or something. Do you have a question? I thought
Any chance you were collecting these at any time?
Why do you ask? I'm curious. Oh, jeez. Are you good? Do you need a Band-Aid? I got one. I'm not going to
It's
collect
a
it.
negative completion grade ending.
I thought you were being sly and trying to be like, oh, I'm just not going to do it.
That's what I thought too.
I have a bunch of Band-Aids in here. I don't know if I have.
Band-Aids in the cash box.
Yeah,
Do you have any lightning between Band-Aids?
No.
Is there any money in there?
No. This is, I don't think this is a bank box because
Yeah, Brody.
It's the first.
actually it might be. There's technically a keyhole, but
And then.
I could rip this apart with my bare hands. So
Yeah.
Do it. Without flipping.
part of me wants to.
and then you can explain.
As
the
a
physics
kid,
of it.
I
Show
love.
us the physics behind it.
As a kid, I loved to destroy things. So and my parents would get mad, so they made me take things apart. So it was basically like ordered this destruction. So like our vacuum broke, I just sat in the driveway and took the whole thing apart. And then I didn't care enough to put it back together, so I just threw it all away. But I do like to destroy things. So part of me is tempted, but then I wouldn't have a Band-Aid holder.
He'd be fun around
Yeah.
the 4th of July.
I don't think you could pull it off. I mean,
Have sticks of dynamite.
My uncles, they live in Minnesota, and they have, my grandpa had a farm that we still own. And so, do you know what tannerite is?
Yeah.
Yeah, they always get tannerite out. Fill a Pepsi bottle with it and throw it out there.
What's better yet? is
Couple things they've blown up with it, but typically they just shoot it and blow stuff up.
Hey, have you ever shot bottle rockets out of your hands?
Oh yeah, I've had bottle rocket wars.
So you like take them, you know, like you just barely hold on to them. You go,
Yeah, we put them in like a PVC pipe, light them, and then throw them in the pipe, and then aim.
well, we took like my cousin and I took like a, I think it was a quarter, it was a half-inch PVC pipe we stuck in the ground, and then we bent it, and we just took a bunch of bottle rockets and just stuck them in the end, and just had their we just had the fuses just sticking out of the end, and we take a blowtorch and lit them, so they're all lit at once, and we pull them back and like slingshot them.
Oh my god.
Not at each other. We just launch them. Or something else is we took a can of Pepsi and we put some gasoline in it, and we stuck a firecracker in the mouth of the can and lit it. So,
You made practically a Molotov cocktail.
pretty much.
Although it's
Alright, how are you guys doing on this?
Yeah.
But we're not fun with firecrackers still. I said it's a lot of fun to play with firecrackers. Just don't forget to let go.
Alright, it looks like you guys need some help with this.
Yes.
We have
So, when we're reading this assignment, right, when we read this, guys, I know it's Friday, I want to have fun, but we also got stuff we need to do, alright? So this one, guys, it's asking us to draw a free body diagram, right? The object is already there. In reality, this is like a boulder, a rock that he's pushing. There's a picture in the top right. We don't really draw details like that in our free body diagrams. We just want to say, yep, that's the object that I'm interested in. I want to know what forces act on that object. Well, what should be your number one answer for what's a force that acts on this boulder? Gravity. That's almost always your number one answer. What direction is gravity going? Up or down? We know it's down. And then we label it, right? You need to identify what force you're describing right here. So I label it F sub G. That's the standard notation for the force of gravity. Is there any other forces that are acting in the y direction? The normal force. This was one that we talked about a little bit. The normal force is literally just basically the force of whatever's holding your object. Right? If I didn't have my normal force, my rock would go straight to the center of the earth. Because that's the only force acting. It'd move it. It'd accelerate it. Well, you have some force that counteracts gravity to keep it stationary. Did I draw my free body diagram correctly? No. It's way badly messed up.
So if something is sinking in like mud, does that mean it would have like a negative normal force?
No, it just means that
There's no
the normal force is because there's constant like pressure in this direction, so something can't go down any further. And so because mud, there's a little bit of like air because it's liquid.
Yeah.
If you fall through it.
You would have some normal force, but the overall force, gravity would overcome, and so that's what caused it to move down.
Okay, so it would be okay.
Yeah. Why is this incorrectly drawn?
Because the normal force is always exactly opposite. Well, not always, but
Yes, not always,
The forces are always.
but in a normal situation, that rock is just sitting on the ground, it's not moving in the y direction at all.
Yes, that means.
Or
whatever
rather,
object
it's not
is, right,
changing its motion. What, John?
Because that object right there would probably be like moving upwards, wouldn't it?
Yeah, if this is what's happening, I have a way bigger force pulling up. This would come this force, and so there would be some motion upwards. So this is not correct. Remember, a force is a vector. It has a magnitude, a size. It also has a direction. Well, the fact that we're drawing arrows is the direction, but the size of our arrow indicates the magnitude of that force. So I needed to draw this. Again, you don't have, on your paper, you have a grid, so you can be precise. Now, if you just sketch this, you have to ballpark it, right? You have to your best of your ability. I'm going to draw this about the same size because that reflects what's happening. These forces are equal and opposite. They cancel each other out. There's no acceleration in the y direction. Now, is there any other force in the y direction? No, there's nothing else acting on that object in the y direction. Right? Sorry, I need to make this a little bigger.
Because there's one on the steps.
Dang.
And apparently,
That kind of fits into the.
How about the x direction? What forces are acting in this direction? Push, right? So I'm going to, again, my notation, I chose to start the force at the object and draw it outward. I need to stick with that convention the whole time. F, we're going to do sub P, right? F, push. We're going to make this one up.
Force.
Any other forces acting?
Force.
Friction. This one, you'll want to get used to. It said a rough horizontal surface. When you see that word rough, that's AP's sly way of telling you, friction's a part of this problem.
So does that mean that, like, if you were to have like a floor that is perfectly smooth, it would have no friction?
That's a good question. Do you think that we can achieve that in real life?
Probably not.
Probably not. You're correct. Ethan was saying, if I have a floor that's perfectly smooth, would it have no friction? It would probably have very low friction, but it will not be complete. Yeah, frictionless does not exist unless you're in outer space.
This. How about what we do
Spend millions
is
of dollars
we
in
go and we buy, like, I don't know, several drums of baby oil and dump it down the hallway.
I can tell you the conclusion of that lab would be you made a mess, and 2, you can't get a frictionless surface.
And 3, you gotta pick it up.
The other, Ethan, the other thing to consider, friction depends on what materials are sliding. My rubber shoe,
There's a lot
and
of friction.
it has a lot of friction. Now if I take a piece of, like,
Yes.
right, oil, if I add oil, I'm now rubbing rubber and oil. Oil's very slippery. There's low friction. So that changes. So even though you could have perfectly smooth rubber, that's going to have a ton of friction
Right.
because it's rubber. Now we're actually going to talk about how we calculate the friction force. We're going to learn about a coefficient called the coefficient of friction. That coefficient describes how sticky or grippy 2 surfaces are. That determines what your friction is. We're going to talk about in this unit.
What if it was
Josh?
like 2 of the same, like 2 types of oil, and they're both like
Really,
hitting
wouldn't they
each
just,
other?
like,
Would they still be having friction on them? Like,
Yes,
like
if you have
each
2
other?
liquids that are having friction, that's called viscosity. You
I thought
have shear.
viscosity was like how.
How
Like,
slowly
like, I
it
thought it
moves
was like
itself.
how like thick.
It is,
Or,
but it's a measure of the friction of your liquid. It's how well the fluid can flow past each other. Right? Molasses, it doesn't really flow well. It can't slide and move around itself. It's thick.
so do solids even exist, or are they just liquids with very, very high viscosity?
No, remember chemistry? Solid, liquid, gas, plasma?
What?
There are distinct states of matter. No, we're getting on a tangent. I need you to stay focused with me, please.
Josh.
Guys,
Soaking it.
We have not gotten far. I need you to focus up, please. This is our free body diagram. We have written and drawn all the forces acting. Now we're going to the next step where we're going to do the math to solve for, right? Blake is asked to derive an equation that relates gravity to normal force. Well, he says gravity to normal force in the y direction. So his first step, sum of the force in the y equals mass times the acceleration in the y. He just literally did Newton's second law. That's how he started his work. His next step, he took the sum of the force in the y direction, and he said, well, the forces in the y direction are this and this. I need to sum them together. This is a positive, that's a negative, so I write Fn minus Fg, right? Fn minus Fg that's what he did. And you would write in the y direction, there's only two forces, the normal force and gravity. Normal force is positive because it's upward, gravity is negative because it's downward. John?
So the weird E next to the F, Y is the sum of the forces. So
Yes, that was that sigma that I mentioned to you guys. Brody, Andre, please focus. Sigma, right? That weird E that John was asking about, that is the letter sigma. It means the sum of. You'll see that a ton. You'll see it almost the rest of this class. All right? What did Blake do in the third step? He crossed something out. What did he cross out?
Crossed out acceleration.
Yeah, he crossed out his acceleration. Okay, sorry, I'll put the first step. Sum of the forces equals. The next step that he did, he said, why did he say the acceleration was 0?
Because it wasn't moving in the right direction.
Yeah, your explanation for what this step is you would say there is no acceleration in the y direction. It's just a rock on the ground. It's not moving up. It's not moving down. It's not speeding up. It's not speeding down. He knows there's no acceleration in the y direction. Its motion is not changing in the y direction. That's what you would write. There is no change in motion in the y direction, so a equals 0. Bam. Well, now, this step is pretty easy. He just did his math. M times 0, whatever mass is going to be 0. So you can write, yeah, M, the mass times the 0 acceleration equals 0. So Fn minus Fg equals 0. You're just explaining the math that he's doing. You're giving the reason why he did this. And then what is the last step? More math, isn't it? This is his conclusion. He was asked, derive an equation that relates gravity and normal force.
They're equal.
He couldn't have done a better job. His math showed him that there is a direct relationship between the normal force and the force of gravity. And so your reasoning would be, therefore, the normal force must equal the gravitational force. What?
On the paper.
Oh, they do FMG?
Yeah.
No. What? It's not really important. It's just nuance. What they're saying is the force of gravity, specifically mass times gravity. So this, right, is the same thing as, this is specifically saying, hey, this force is mass times gravity. Right? I would always write Fg. Just, the force of gravity. When you go to calculate it, gravity is always calculated by mass times 9.81.
the difference between cancel with 1L and cancel with 2?
You want to spell them correctly?
Alright.
Because I wrote cancel on the ticket, and now I'm trying to figure
What I want you to look at on the back side, look at Blake's statement that he made. Go to the back of 2C. Blake said the velocity of the block, right? This is a different scenario. We have this block. It's got gravity, normal force, friction, but he's pulling up at an angle. It said the velocity of the block is constant, so the net force exerted on the block must be 0. Thus, the normal force, Fn, equals the weight, Fmg, and then the force of friction equals the applied force of F pull. Is there any parts of his statement that are incorrect? Yes, there are. Let me see where it says. Let me get the projector up so I can show this.
That's the big answer.
Yes, they go all out. Whoa, hello. Right, here's a statement. Let me get these two. Is the first sentence true? The velocity of the block is constant, so the net force exerted on the block must be 0. We got this. The instructions told us, hey, this block goes at constant speed,
Yeah, net force.
so this is good.
The net force is 0.
What do we think? Is the net force on the block 0? And here's some. I see some conflicting answers.
No, because wouldn't that mean it's not moving?
Well, which means it wouldn't have acceleration.
Let's go back to Newton's second law.
It would stay in motion.
This is Newton's second law. The net force, right, adding up all the forces, whatever's left, causes an object to accelerate. We're told that it moves horizontally at a constant speed.
So it's not accelerating.
So it's not accelerating.
But the net force is 0. That's horizontal. Right?
Yeah, we're looking at horizontal direction. Yes. Constant speed, that's not accelerating.
Yeah, we're on.
So in the horizontal direction, we know this is true. The net force is 0. How about the y direction? Is this true?
That's not.
It didn't specify a direction.
Net force is not 0. The y direction is not 0.
How do you know, though?
Because he's pushing at an angle, and so if you break that down, the x's are equal to, you've got the normal force of gravity and then a little bit going up.
Right.
So when you add all those up, it's a little bit going up.
How do you know? Ethan's talking about if you add this part in the y direction, this and this, you get a little bit going up. Is this block moving in the y direction? It tells us it slides along the surface. Well, is it sliding up? Is it sliding down? No. Its position's not changing in the y direction.
So is gravity larger than the normal force in this case?
So that's one. So Ethan, you're right to see, like, there's some part where you're pulling up. A little piece is pulling up, normal force and gravity. However, we would have to actually do our math to figure it out. But we know from the scenario that this object's not moving in the y direction. So we can conclude, because of Newton's second law, that this is the sum of the force in the y direction is also 0. So that means his statement, this is true so far. The object is not moving or accelerating in the y direction, and it's not accelerating in the x direction. So that means any direction you look at, the sum of the forces is 0 because there's no acceleration. So this first statement's true. Even this is where you're talking about the components. He says the normal force equals gravity. Now that's not true because Ethan's right. Some part of your pull is upward. Well, we know they all have to add up to 0 in the y direction. This little pull plus this has to equal this. Well, that means automatically these can't be equal, because then this little piece would have to be 0 for this plus this to equal this. So this is baloney. That's not true. Do you see why? I have these two pieces have to balance this piece. Well, if that's true, this cannot be the same, because then this little piece wouldn't matter. How about the second part? Same concept. He said the friction equals the pull force. Is that true? He said this equals this.
Oh.
Yeah, that's not true. This object is in constant speed. Therefore, any force in the x direction, they're equal and opposite. Well, if he said this and this are equal, that doesn't make any sense. Because in the x direction, I only want this force. What this force is Fpx. The component of this force that acts in the x direction, that is equal to the friction. Because that's the only thing acting in the x direction. So this is also not true. Do we follow that? One thing that we're gonna start doing a lot more of is you're gonna get a problem like this. And you're going to ask to solve this, find the values. So what you're going to do is you're going to do sum of the force in the y direction equals mass times acceleration in the y direction. We know this is 0. What forces are in the y direction? Well, I have Fn, which is positive, Fg, which is negative, and then a component of this force I need to include that. So then I would add F pull Y. Do you see that? You're going to start using Newton's second law to solve for the forces. You're going to, like Ethan's right, recognize this has components in the x and the y. I need to do remember my vector worksheet? I need to figure out this angle and do my trig and see, hey, how big is this? How big is this? That lets me include it. You also do another summation. You know the acceleration in the x direction is 0 because it's constant speed. It's not accelerating at all. Well, that means the forces that I have in the x direction, I have a negative force or friction, right? To the right is positive x. This is negative x. Then I have this, plus force pull in the x direction. So you would do, cosine of this degree equals opposite, right? SOHCA, TOA, adjacent over hypotenuse. Do your math and figure out what this is and plug it in. And you realize force of friction equals balances the pull in the x direction. Do the same thing. Normal and the upward force balance out gravity. Does that make sense? Don't worry too much about the explanation, because we just talked about explaining why those statements are incorrect. Again, this is where we're headed. We're going to start using trig, right? Resolving a force vector into its x and y components. And then we're going to do this. Sum the force in the y direction. That's equal to the mass times acceleration. Sum the force in the x direction. That's equal to the mass times the acceleration in the x direction. We're going to do this a lot. This is a huge piece of physics. Again, we'll do it step by step. We'll start small. Any questions on that one? Did I lose you guys? Do we track with this? Does it make sense? So? Remember Newton's second law, F equals ma. We have two main directions, that's why we had to do it twice. Then all you do is figure out what forces are in the x, what forces in the y, add them up, and they equal ma. That's the generic process. Alright? So then, I want to get through want to do Newton's third law now. Newton's third law is pretty straightforward. It's, again, an extension of the others. They're all related, but they're distinct. So that was 2.c. Newton's third law. Right? What's that?
Oh, done with this for today?
Yeah, the workbook, I only wanted to finish that last sheet. Now I want to explain Newton's third law. Right? What was Newton's first law? Aiden's got it. Object will stay in its motion unless some force acts on it and changes its motion. That also means it will literally stay there forever until some force causes it to move. That was Newton's first law. The second law, F equals ma. Particularly, the sum of the forces, right? The net force equals the mass of that object times its acceleration. Do you remember those relationships that we got? If you increase the force on an object, you increase the acceleration. If you increase the mass of whatever object but keep the force the same, it's going to move slower, so your acceleration goes down. Right? What we're at now with Newton's third law is basically for every action, there's an equal and opposite reaction. You heard that before? Probably rings a bell. Heard it in movies or shows, whatever. That's what Newton's third law is. Every time there's some action or force, there is actually an equal and opposite reaction. You know gravity, right? Gravity is this strange force that pulls other objects to itself. Did you know that we have gravity? Me as an object, I have gravity. Just as much as gravity is trying to pull me to the center of the earth, I am trying to pull the earth to the center of me, the center of my mass. Gravity is just this weird attraction between mass. Did you know that when I jump up, I accelerate a certain amount? Did you know that the earth accelerates a proportional amount downwards? Did you know that? Right? When I jump off the ground, I'm pushing off the earth, aren't I? And accelerating myself upward. As soon as I push off the ground, did you know I push the earth down in equal and opposite amount? And that causes the earth to accelerate downward? Did you know that?
That's what causes earthquakes.
Is that a fat joke on me? You think I'm causing earthquakes? Rude.
So every person on earth to go to one spot and we all just jump at the same time, can we knock the earth off its axis?
That is a very common mind or mental exercise. Aiden was saying if everyone in the country stood on a chair
World.
and at the same time jumped and landed at the same time, if all of us landed at the same time and caused a huge force, could we move the earth out of orbit? I don't know if you can. I don't know if our mass is nearly
I
enough.
watched a video about it.
You can't? Yeah.
So
They said it wouldn't even do anything.
Yeah, it's so small.
Yeah.
Now, the reason is, right, if I'm saying for every action there's an equal and opposite reaction,
What if we all blow it up to 800 pounds each, and then try?
Because I feel like it's that. I feel like a nuke is much more powerful than 300 million people laying on the ground.
You wouldn't be able to stay on my chair.
I'm just saying theoretically, I feel like that a nuke would have a lot more of a force than
Didn't even know it.
300 million people laying on the ground.
do you guys see this? I'm giving you a representation. If I jump, I'm pushing off the earth, right? The earth pushes me up. I'm also pushing the earth down. These are equal forces, equal and opposite. However, I don't have a lot of mass. So that force causes quite a bit of acceleration. That's why I can jump up. What about the earth? The earth has ridiculously more mass. So the same force on a huge mass does almost nothing.
Wait, when you say it would have more inertia, is that what you said?
Yes, the earth has an enormous amount of mass or inertia. Any force that acts on earth, it can resist that force very well. So if you can look up the numbers and do the math, and you say, hey, if I jump with 20 newtons of force, you can calculate your acceleration. Well, you can do the acceleration of the earth. It would be like 0.00000000002 meter per second squared or something. Right? Every force has an equal and opposite reaction. We act on Earth, but it almost does nothing.
Ouch.
Why did he fall over even though he kicked the car?
Because he lost his balance.
Because he pushed himself away from the car.
Newton's third law. Why did he fall over even though he applied the force?
Because
the car kicked back.
The car kicked back. He applied a force on the car. Every force has an equal and opposite reaction. So when he's kicking, the force he puts on the car gives back.
in America, you kick the car. So much rough the car kick you.
It's like a reference people say, like, you're gonna kick the can or something like that. I don't know.
Kick the
Like he
bucket
died?
when you die. Yeah, that's when you die.
What happens when the bucket gets back?
I don't know. But anyway,
I think that's the point.
this is just like my example of me jumping in the earth. He kicked with a pretty good force. Well, he's kicking a car. The car weighs like 4,000 pounds. His kick isn't going to do much. It has a ton of mass. It can resist that force really well. He might nudge it like a centimeter over, but that's it. But the car kicks him back the same. the equal and opposite reaction. He's not very big. He's on a little moped. So the force that he kicks, he doesn't have enough mass to resist it, so he accelerates the other way. You see that?
You seem like the guy that says, yeah.
The bucket kicking back.
Yeah, I thought you didn't survive that one.
Nah, he probably did.
Yeah.
Then he went under the tire of that second car.
Yeah, that's actually a really scary scenario.
Yeah, I feel like he definitely got stoned for that.
Oh.
Wall push-ups.
Oh, I thought
Right?
that one thing with the chair.
When you're on the wall, you're pushing on the wall. That's how you push away from the wall. Do you know that wall pushes back on you?
Yeah.
That's why you move backwards.
It's a blind.
This reaction is the reason you go backwards. Right? I'm pushing on the wall. The wall has a ton of mass. It can resist it. It just stays there. But the wall pushes back on me. I can't resist that force. That's why I can push back.
So technically,
Does that
if
make
you run
sense?
up and you push someone that's much larger than you and you fall down, you can technically say they pushed you back. And you can sue it.
Technically, you could cite Newton's third law and say, they pushed me back.
You guys are giving me ideas.
Now, granted, you initiated the force, and there was simply a reaction.
Yeah.
So they're not actively pushing you, but they did.
Look at like, so
So next time, I can actually just say, no, officer, that child actually punched me.
That's a horrible example.
Bunch of kids.
Hey, he's not over 18 yet, right?
Aiden's getting dark. All right, you guys. Which force accelerates the car to the right? Does the engine's force push it to the right? Does the force of the tires push it to the right? Or does the road push it to the right?
I'm going to say the road.
We think the road? Tire?
Wait, what?
I'm
I
confused.
got no idea.
I can't see the option.
The engine, the tires, or the road? Excuse me. Which one of these is actually pushing it to the right? What is this?
Friction.
Yeah, it's friction.
Dying.
Isn't that the tire rotating? It's rotating this way. It's trying to go this way every time. Your tires are actually trying to push this way. What's this? If I push on the road this way, what does the road do to me? It pushes me forward.
Big one.
Right? When your tire spins, it's trying to go this way. It's trying to push. When it's spinning, it has no resistance, so then it just keeps going. But in a normal circumstance, there's enough friction that the friction can oppose it. The road is actually what pushes you forward.
So technically, like when you get stuck,
Isn't that weird?
because you don't have any friction.
Yes. That's why you put sand down. If you're stuck on the ice, you put sand down to increase the coefficient of friction. Ethan, the coefficient of friction, rubber on ice is very slippery. You don't get friction, so you don't have traction. When you put sand on that ice, it adds roughness, increases your coefficient of friction, so you have enough friction to actually rotate.
Or you just lay nails down on
Yeah, or you have spiked tires. Also, this is really funny. Who painted this?
Yikes.
No, it was like one of the Instagram ladies who like took a picture by it or whatever.
This would be one where you like have
Like the doors,
you
like,
had one
doors.
job.
The person was trying to slow down, and the pain was trying to go with them.
All right. Which received a larger force? Did her foot receive a larger force, or did the ball?
Would it be the same?
I'm sorry, I'm completely distracted by the woman's face in the background.
Oh yeah, they'd be the same.
Remember, we're talking about Newton's third law. Every action has an equal and opposite reaction.
They were the same force.
When she kicks that ball, the ball is kicking her back, right?
But the ball doesn't have much inertia, so she can like send it.
Yes.
Compared to like if that ball was a bowling ball, then the ball wouldn't go very far.
Josh is exactly right. Remember when we talked about mass and inertia?
Yes.
When I kick a soccer ball, my leg has a lot of mass and a lot of energy. I apply that force. The ball doesn't have a lot of mass. It can't resist that force, so it shoots off. Now my leg can resist it pretty well. If I kicked a bowling ball is not going to go very far. I'm going to get hurt more because that force, right, the full force that I kick gets returned. Because it resists more, I take more force to push it, so it hurts more. This video won't play, and I'm super mad. This was supposed to be like an epic tackle.
Oh,
And
just look up hard hits in the NFL on YouTube.
Those are.
at the end of class, I can look those up.
Wait,
The codec won't play, and I don't know why.
I think there was like a hockey game this past week where some guy, he got hit, like the goalie got hit in the neck by the puck.
No.
Okay, right here.
He had his helmet, had his head tilted up, and it came into his lane.
Okay, let me focus. Let me get through this, you guys. The Earth is pulling the astronaut down, right? Gravity's still acting. It's trying to pull that astronaut down. Do you know the astronaut is trying to pull it up? Remember I told you? I have mass as an object. Every single object with mass has, gravity. They're equal and opposite. This is the example. He weighs 71 kilograms. He weighs 5, almost 6 times 10 to the 24th kilograms. Literally 24 orders of magnitude larger than my mass. The forces are the same. But the acceleration, I don't know if it'll do the math. It's right here. This force on the Earth, 10 to the negative 22nd. There are 21 zeros in front of this number. That's the acceleration of the Earth. It's physically insignificant. Huh?
Then it's not really cool.
Yeah, it is. It is, but it's so small, you will never notice that. I mean, this is like, I think, smaller than nanometers. This technically might be, this is a billionth of a nanometer per second. Right? That's absolutely ridiculous. The velocity of the Earth increases by a billionth nanometer per second every second. It's insignificant. Yeah, there's all the zeros. I think this is one where it says, hey, if all these people jump, the entire population of the Earth, 7 billion people, you only get to here. The acceleration of the Earth is still this small, like 10 a billionth a nanometer. It's crazy. You know, you guys, anybody hunt or shoot? You guys know what recoil is?
Yeah.
When I shoot a shotgun,
The gun shoots
right?
back.
It shoots back. Have you ever shot a gun that was maybe more powerful than you're used to? Your shoulder hurts. Because every time you shoot, it recoils and hits your shoulder. That's because the force that you apply on the bullet to send it out also gets applied on the gun.
First time I ever shot a gun, it had a scope and I got a black eye.
Yeah. When you hold it, you look through the scope and it shoots back and hits you in the eyeball. Guys, what experienced a larger acceleration, the bullet or the gun?
They're equal.
Acceleration, the force is the same. The bullet. Why?
Because it's such a small mass.
The mass is small. F equals ma. If I have the same force and my mass is teeny, I have to have a huge acceleration. If I have a big mass, I don't have as much acceleration. F equals ma. Yeah, there's a good visual representation. Forces are equal. The bullet's mass is teeny. The gun's mass is huge. Well, if I keep this the same, make this small, this big, these go the opposite. huge acceleration, tiny acceleration. Who received the larger force?
Same force.
They're equal.
They're equal.
No, I bet, yeah, right.
He's kicking, he's applying the force, but this guy has inertia. He resists the force and he pushes back. Equal and opposite reactions. This looks scripted to me. I don't really buy this.
I don't buy it for a second. Unless this kid is insane.
Also, I don't know where her foot is.
It's like, he's like in front of her, something like that.
Yeah, that looks like some acting. Here's a crazy statement. McKay, Joey, can I be focused? I'm almost done. Do you know it's impossible to punch a piece of paper with 50 pounds of force?
Oh, because it can't give 50 pounds force back or something.
Andre,
Smart
hit the
boy.
nail on the head. That's exactly right. Andre said the reason this is true, the paper can't push back that hard. So if I could punch with 200 pounds of force,
So rock.
Dang, bro.
right?
Okay.
Dang.
If I'm Muhammad Ali, right?
No,
If I can hit some just money make right,
That's
waylay
I'd
people.
drive 'em.
It doesn't matter because whatever force I apply on the paper can't give it back.
Right.
So here's the math to show you. This is how fast that paper would have to accelerate in order for it to give you 50 pounds back. You would have to, this is like 5,000 G's. Right? This is a comma. I'm sorry, it cuts it off. This is 50,000 meters per second squared. You would have to accelerate that piece of paper 50,000 meters per second every second. Yeah, it's ludicrous. That is literally 5,000 G's. 5,000 times the magnitude of gravity's acceleration. Ridiculous. This is why you can't do it. You know what's going to happen here?
Oh, this is funny. I love this.
So this, when it has audio, it has the Imagine Dragons song, Sail, and then I don't know if I can play it. Bam! Is it not?
I don't think so.
No, I don't
Who sings that song?
What
It's
song?
The Sail, right? Sail!
It's so imaginative.
Did I get that wrong?
I feel
Oh, no.
Okay, you guys shouldn't have your phones, but I'll let you for this.
AWOL Nation.
Yeah, guys, I see them.
AWOL Nation.
AWOL Nation.
Same thing.
I was wrong. We got 10 minutes. Can you hold it? Okay.
But have you seen the video where the cat's like walking across the thing, and so they all just press the horn and just
Right? Action and reactions, they don't always cancel each other out. That's not what's actually happening.
Is that why stubbing your toe hurts so much?
Do you see this? This
What's that
force
your toe? You stubbed the table.
pushes this way and there's a reaction.
You accidentally
This
take
force
the table
pushes
with the
this
table
way and there's a reaction. The reactions aren't canceling each other out. The opposite actions are canceling each other out. Do you see that? It's not me kicking the ball and the ball's reaction negates stuff and causes it to not move at all. It's the other force in the equal and opposite direction that cancels it.
Can someone who's a former soccer player explain the color of that ball?
No.
Really like a game.
Right? If I only kick the ball's reaction doesn't cancel the forces. I apply a force on that ball and accelerate it. The ball puts a force on me and accelerates me, which is really just slowing my kick down. This one gets a little crazy. This is where we get to, remember I talked about the system of your objects, right? How you define your system is important. We're going to place all of these forces, right? The horse is moving forward. It's pushing this way. Well, the ground pushes back, doesn't it? That's what moves you forward. If I push on the ground and I can't move it, the ground's going to push back on me. You bet the ground can actually push me forward. The horse pulls on the cart, right? It's pulling the cart. The cart pulls back on the horse. Bingo. Right? The cart is pushing on the ground, or the wheel. The ground pushes back on the wheel. Now, if I look at the total horse, how much force is acting on that horse? The ground has 300 newtons on the horse. The cart pulls back on the horse with 100. So what's the net force on the horse? That didn't mean to rhyme. That's pretty cool that it did, though. 200 this way. Right? How about the cart? What forces are acting on the cart? The horse is pulling on the cart. The ground is pushing back, friction on the cart. So you have 50 total, right? Negative 100, positive 50 gives you negative 50. These are two systems. This is one system. What acts on it? This is another system. What acts on it? What happens if I take this to be my system? I want to imagine that this is one object. Well, you need to say, what acts on this? Well, the horse on the cart and the cart on the horse, they're a part of the same system. So we don't care about that. Nothing is acting on this because it's between the two. Right? These net forces don't count anymore. We only want to look at the forces on the bottom. Right? The ground acts on the horse, which is a part of this whole system. The ground of the wheel acts on the cart, which is a part of our system. Those are external forces. So I do negative 300, positive 50 gives me negative 200. If I look at the acceleration of my horse-cart system, I would do F equals ma with this force. The net force on my horse-cart. That's the object I'm considering. The mass is this plus this, and then I calculate what's the acceleration of this. Does that make sense? This is important because this gets to back. I talked about introduce, I guess, the system. The system is what you're considering, what you're trying to calculate. AP might ask you, what is the net force on the horse? I don't want this. I want to go back and say, these forces act on the horse. It could ask you a follow-up question. What's the net force on the horse-cart system? You're like, hey, what things act on this whole body? Well, the only things acting on that are these. These forces are called internal forces. They happen between the objects that I'm grouping together. I don't care what they do. They're a part of the same thing. Does that make sense?
Yes, sir.
Good? Newton's first law. Every object in motion will stay in motion unless it's acted upon. It's going to stay there, stay still until some force acts on it. Second law, F equals ma. We want to look at the x direction, F equals ma, and the y direction, F equals ma. Newton's third law, what we just did is every action, there's an equal and opposite reaction. The reactions don't cancel out the force. It's just a reaction on that returns to you, right? So what I have on Classroom, I have a couple problems I want you to do for the weekend. It's only like 5. So what I want you guys to do, there's a couple pages I want you to read. 4.4 is Newton's third law, I'm pretty sure. 4.5 is like forces. So I want you to do both of those. This is specifically 2 problems on Newton's second law, or third law. And this is 3 problems on just general force, sum of forces, right? So I just want you to work on these 5 problems for the weekend, turn in for next class. Reminder, I'm going to grade these on completion. You need to, when you come to class, you're going to have to show me, Mr. H, here's my homework. I'll mark it off, give you all points. Then we can talk about it, see what questions you have, address the confusing ones, and make sure you understand, like, yeah, Mr. H, I had no clue how to do this one. I don't think it's right. Can we confirm how to do it? Absolutely. We'll take a little bit of time to do that, and then we'll get going with whatever we have for that day. All right, any other questions? All right, let's do, what do you want to look up? Epic football hits? Some of these are pretty brutal to watch, actually. Oh.
What the heck?
Oh yeah. Wait for it.
Oh, yeah. Oh, yeah.
Ooh.
It always finds out.
And Sanders got killed.
Oh my gosh.
Yeah.
Oh.
I like seeing Steelers.
Oh my gosh.
That satisfies my soul. When
Oh my gosh.
players get knocked on the ground.
So this is crazy to think about. However hard the person getting tackled gets hit, the person tackling feels the same force.
But you see someone, they hit them, they keep going.
Yeah, that's, again, we're going to get to momentum and energy, right? Here, I'm going to... Oh, jeez. So did you see that hit? This one right here? So Josh, you were saying when they tackle, the person that tackles them just slows down a little bit. The person that's standing there throwing the pass and then they get waylaid, they get launched back, right? Same force, except I have a bunch of speed and my force, right? I'm tackling someone. I'm tackling them. Well, if they're at a standstill, that force is going to accelerate them back.
You can be accelerated back the same amount, but you're already moving forward.
Yes.
faster than that.
When I'm running to tackle them, I'm going to get accelerated. They're going to push back on me, however hard I tackle. I'm going to accelerate this way. But I was already running like 5 miles an hour. All it's really going to do is slow me down a bit. It's also going to touch back to, you guys in particular always ask the questions that are related to the momentum and energy. Who had more energy in the tackle? The guy standing there or the guy running full speed at him?
Gotta run full speed.
Yeah. He's got a ton of energy. That energy also impacts the effect on the 2 objects. It's kind of like my car example. The Tahoe has a lot more mass at the same speed than the smart car. You have more mass and velocity, yeah, you got a lot more energy. You win because you have more energy than the other. I guess I'll just let some of these play. This makes you feel bad for wide receivers.
Please.
Yeah, I'm pretty sure he broke his back that way.
Oh my.
Well, the way he just kind of like stood there and then
Oh.
There's no
He
way.
did break something.
From Whitford's fantastic.
Oh,
He's just dirty.
That was a punter. Was that a punter?
That was illegal.
yeah.
That's all.
Oh,
He said, "I don't know what happened."
oh my
Marcus
goodness.
Kill. He just did that to a tight end.
Dang.
Did you see
Hey, he hit her.
Hey,
There's Troy.
what's this?
John Taylor.
Man, these are savage watching them back to back.
Caught him by the
Oh.
What's that? D1.
Oh, yeah.
Big.
Go for it.
So at my high school was the Ankeny Hawks. Our football team had an unofficial award called the Dirty Hawk Award. That's when you get a hit like this in a game. They give you an unofficial, like, secret award to the player that hit, tackled like this. It's pretty skeevy.
No, go back.
You let my boy get the ball.
We let Big Double Zero get the ball.
Big boy.
So this, again, yeah, John, who has more mass?
Quite honestly,
Where is he?
big boy in the
Right
middle.
Right here?
How do you not see
You bet he's got a lot more mass than the other guy.
It's a suburban versus mini
Oh.
Freaking Andre the Giant.
Yes, Suburban versus Smart Car. He's way more massive, right here.
Hey, my suburban, that's suburban.
So this is literally why it's dangerous. You want to be the Suburban. You do not want to be the Smart Car. I don't care how strong your skeleton is, you still take a ton of damage because you're going to get swung backwards.
Hey, that linebacker's like,
Oh! He doesn't even slow down!
Flex, I can't fix that.
Yeah, it's literally physics. Football is all physics.
Oh my.
Right? How much force can I throw? Hey, wait. If I'm a quarterback, what angle do I always want to throw at?
45.
45. Why?
Because you get further.
That angle gives you the maximum distance. If I have a limited arm strength, I want to throw at 45 to maximize the distance. When I throw Hail Marys, I don't want to go like this. It's just going to go up and then down. It's going to go 20 yards. I don't want to throw like this. You're going to go 15, 20 yards, whatever. I want to throw at the 45.
You throw it hard enough like that.
Well, but you have a limited arm strength.
Yeah.
I can't have infinite arm strength to just throw a laser 70 yards. It'd probably knock out your receiver. Right? When you're running, why do they have cleats?
So you can step on people.
Right? You increase your friction so that you can move faster. Right? You can apply a lot stronger friction forces to change your motion better. That's why they use cleats.
I'm ready to die.
Oh.
Imagine playing on a baseball field.
Actually, it wasn't the baseball field. It was the
That
Raiders.
was the Chargers, wasn't it?
No, that was the Raiders.
But I thought the Chargers had that. They played on the baseball field.
Ella Ward.
Are you sure?
Ella Ward.
I swore in the past it was the San Diego Chargers that always played on
they
the.
changed it to the what they changed it to.
Okay, it changed.
Yeah.
Okay. So I wasn't completely insane. Okay, it's just been a while. Again, I don't follow sports at all, so I'm like 10 years outdated. Have a good weekend, Maggie.
You too.
Thanks.
We're watching football with Garrett.
Physics, man. Should we show him Bubba?
Big boy. Big Double Zero.
Where was it?
Oh, right there. Wait, hold on.
When I hear Bubba, I think of Bubba Wallace, golfer.
The big number at the big S in the middle of the field.
Where was it? Oh, here. Watch this. For some reason, this guy gets the ball. Right here. Bam! Just mows him down. I was telling him that's like physics. If you're running at the same speed, you want to have more mass, because then you got more energy. I was explaining that's why parents a lot of times buy their first kid, they buy them a big car, like a Suburban. The only reason they do that is for safety. If I get in an accident, my Suburban is going to win against the smart car, because I have more mass, more energy, that it doesn't really affect me as much as in a smart car. Damn. Okay. At 1:30. Okay. Yeah, give this to me whenever you head out. I'll do attendance first.
What were you doing over there? Breaking shoes.
We were getting concerned.
Yeah, we're breaking shoes. Ooh, I got Mr. Brian. I didn't really think of that. It's like I need a hammer, man. He do grade checks once I get up, and he's got all caught up on his stuff and proves it.
Okay. Do some makeup work and stuff.
Well, I don't know. It's just once you check it up.
Oh, yeah. Do it. Okay.
Oh my god!
Okay, I'll do it.
That nigga just got smeared.
Come put that
Why
on.
you know like that? I'm telling you, I'm putting out the blicky on that.
Yeah, I got nothing for today.
Oh my god, bro! I gotta show you.
So this was carryover from my physics class. We were talking about Newton's third law. Every action, there's an equal opposite reaction.
Why put this on your face? This kid's 6 years old.
I mean,
That ain't fair. Oh! That kid's half his size.
Oh, he's like 6 years old.
That's ridiculous. Oh, wait, I still got the recording going. Whoops.